Okay, anyway, so I said we did it early, but that's a lie, because I talked about this stuff. So, let's see. What I wanted to do today, and I mentioned this last time, is prove PV equals nRT, which sounds like that sucks, and it does, kind of. But the point of this isn't to prove PV equals nRT, is to make sure that you know that what you saw in undergrad, if you saw what I dish out, which you probably did, is here's Boyle's law, pressure proportional to volume, 1 over volume, I think that's Boyle. And then Charles's pressure is proportional to temperature. Yeah, temperature or volume. Volume, temperature, yeah, something like that. Anyway, and you kind of put these empirical relationships together, and you can kind of come up with that PV is proportional to T. And then Avogadro, when they started figuring out that there were molecules, that N was in there, this Avogadro's hypothesis. And I say proportional, to get the units to work, you have to put in some kind of correction factor. That ends up being the gas constant. Okay, that's not a proof. It's not a mathematical proof. That's a bunch of empirical observations kind of slammed up on top of each other. It's not a proof. Today you will see the proof. So the point of this is to kind of get that through your head. The other is what is statistical mechanics good for, and the third thing is the grand canonical ensemble. So I told you that there are more than 2 ensembles. We started with the microcanonical, then we did canonical. Canonical is very intuitive. Remember, that's the one that allows temperature to fluctuate. That's the one that you calculate partition functions, which is the sum of states e to the minus energy kt of, and with that canonical partition function you can calculate anything. It's very intuitive, but there's a third, and that is the grand. Not really that grand. Grand canonical ensemble, and I'm going to start like I did last time with a Legendre transform of entropy over kT, and where am I in my notes? Entropy over kV, sorry, not kVt. Okay, now entropy, of course, over kV is Ln number of microstates. And to Legendre transform away its dependence, entropy's dependence on internal energy. I do a Legendre transform. I subtract the thing I don't like its dependence on times the conjugate, which is 1 over temperature. Okay, now I'm going to do something new. I'm going to Legendre transform away another dependence. Entropy is also dependent upon N, the number of molecules. Entropy is dependent on N, and I want to transform that dependence away as well. Now, where that comes from, by the way, is the fact, let's go back to basics. Normally I wouldn't do, it's not in my notes, normally I wouldn't do this. But I think you may have forgotten some of this. Okay, change in internal energy is work and heat. That's what that is. But one thing we leave off initially with this class or any other is this term. Chemical potential times change in moles. We always start any thermo class, even graduate thermo class, assuming that the box is, we're not going to let gas leak into or out of the box. That would suck. That means I have to add a term if I start adding or taking away gas. And so I assume that I'm not going to do that and I can simplify things. But it is there. It needs to be there for when we talk about chemical transformations, reactions. Or I'll start out with ice melting because that's a lot easier. Ice melting is a legit reaction, actually. It's brainless, but it does count as a legit reaction. And then we need to have these terms in our thermo. Okay, now, and I don't remember if I mentioned this to you. I thought I did, but I may be fooling myself. Internal energy is different than all the other energies because everything is extensive. All the partials are extensive. That means they can be integrated from 0. Right, you can have 0 volume. Pretty sure. You can have 0 entropy. You just have to have a perfect crystal. You can have no molecules. And you can fill the box such that there are N molecules with S entropy, and it'll have V volume. So all this is integratable. Okay, I just want to point that out. Now, since G is U plus PV minus TS, G ends up being chemical potential times number of molecules. Now, this is all just literally middle school math, but it does point out why our A's and G's are a bit more important than H's and U's, because they're inherently more sensitive to chemical transformation. I'm going to use this in the proof, by the way. That's why I'm bringing it up. Okay, anyway, back to task. Here is a new statistical definition of entropy. And I'm not going to do the proof, but it ends up being almost identical to the canonical. Everything that we do to derive, to work in the grand canonical is identical to the canonical. So I'm not going to bother to redo the proofs, but we're going to end up with a grand canonical partition function. Remember, there's no partition functions in the microcanonical. Microcanonical is a little funky that way. Canonical, we have partition functions, and in the grand canonical, we also have partition functions. And unfortunately, it gets this stupid symbol, and ends up being states, a sum of states, and that is actually, maybe you don't recall the derivation of the canonical partition function, but the sum of states is hiding in entropy. This is why you don't explicitly see S in any of these partition functions. S's job is manifested by the sum of states. Okay, this is the canonical partition function, but the grand canonical picks up this term. Okay. So, okay, now back to this guy. Entropy is dependent upon n. So in the microcanonical, n is fixed. Now I'm Legendre transforming it to work in the grand canonical world, and that means that n is not fixed. Chemical potential is fixed. Chemical potential is conjugate right here, right? This conjugate of this. When you Legendre transform away, this is no longer fixed, instead the conjugate is. Okay, in grand canonical world, chemical potential is set, n is not set. So the idea is that we're going to describe a system at a constant chemical potential, and to keep the chemical potential constant, what you do is you add or take away molecules. Now this is analogous to the canonical where temperature is fixed. To keep temperature fixed, we might have to take in or add thermal energy. That if it naturally gets a little cold, we have to heat it up a bit to keep the temperature constant. The microcanonical, which it works at constant U, temperature fluctuates. Anyway, I'm kind of working backwards, but there you go. That's the idea. So again, we're in a world of constant chemical potential. And like all the partition functions, we have these because solving certain problems is easiest done in certain regimes. Last time we talked about two-level systems in the microcanonical, and I showed you how you can't ever populate a two-level system beyond half. And the microcanonical derivation took a while, but it was doable. In the canonical, it's actually a bit easier, but I didn't do that one. We just kind of pushed you a bit. The grand canonical is a good one for doing PV equals nRT, so that's why I'm doing it this way. And the probability of a state, of the state's existence, certainly looks like the canonical. It feeds the energy over kVt, but it picks up a extra term. Okay, so again, it's very canonical looking, except that it just simply has this extra term there. It kind of messes, it just makes it looks a little harder. Okay, so let me show you some properties of the grand canonical partition function. Let's see, what do I want to do? So again, it's very much like the canonical, and so when I had the natural log of the canonical partition function equaling Helmholtz energy, which again is very useful. Now what I want to know is what's the natural log of the, oh god, this is such a pain, right? What is that equal to? what is the natural log of the grand canonical partition function? And again, I'm going to use this in my derivation. Okay, now to do that, I don't think I have the room. Yeah, I need the whole board to do this. Okay. Need the whole board. We're going to use this old formula, Gibbs entropy formula. Space, EV, ln, where the probability of the state is defined right here. And what we end up with is minus KB, where am I at? Sum of states. Now always we leave one probability alone, and then we do the other. And we end up with this natural log of the partition function, minus natural log because that's on bottom. And then plus what's on top. What's on top is a minus beta internal energy, and what's on top is a plus beta chemical potential fluctuating number of molecules. Okay. Now, the sum of probabilities times, let me just write this out. There's really nothing to this. Okay, this is a number. It's equals something important in thermodynamics, like energy. We don't know that yet. It is just a number, though. So minus a number times all the probabilities you can factor anyway. It just ends up being plus ln grand canonical partition function minus plus KB, I forgot there's a, KB beta average internal energy. Again, that's because internal energy fluctuates in the grand canonical after the grand canonical, and the minus actually survives this time. Okay, so there we go. And this is all entropy. And now when I'm remembering that I'm trying to do this, I've actually got a bit of a problem, is that I'm stuck now. So now what? Now what actually comes from here? Chemical potential times N. Oh, God, I hate this. Is Gibbs energy. I just showed that a minute ago. You see, I planned ahead. So I can plug that guy back in. U plus PV minus TS. But anyway, okay, so S. And you see why I needed a little bit of room. KB, ln, grand canonical partition function plus KB. Sorry, I'm not writing this linearly. Okay, minus, oh God, where am I at? Minus KB, beta, is that, yeah. Okay, now again, chemical potential times average N is average U minus TS plus PV. Okay. Now, it should be kind of obvious that, let's see what I've got. Here we go. S is KB, ln. Obviously, I'm in a canceling situation. Let's see, what can I cancel? Here and here. Now let's see, plus beta KBTS. Uh-oh, what's beta KBTS?
It's just S.
Just S, that's right. Right. Remember, KB is 1 over TS. Beta is 1 over KBT. Anyway, blah, blah, blah. Okay, plus S, where am I at in my notes? Minus Ka beta PV. Okay. Bit of a situation. S is equal to S and a bunch of other stuff. What do you do? There
These
you
are
go.
equal to 0.
Yes, set this equal to 0. Therefore, KB ln grand canonical partition function minus KB beta PD is equal to 0. There's a lot of thermo proofs that rely on this. I haven't gotten a chance to show you that. And therefore, again, I just don't have much room on this board. ln of the grand canonical partition function is equal beta PD. There you go. Okay, so anyway, properties of the grand canonical partition function. I'll use this, I think I use this as part of the proof. I don't know that it has a heck of a lot of meaning in its own, except that I can use it to prove things that are kind of cooler than that. So with that, if all of you got that down, stuff like this is not, natural log of the canonical partition function is minus beta A. That stuff is not really useful. This isn't something like when I'm doing that stupid model I was running my mouth about. Oh yeah, wait a minute, the natural log of the canonical, no, that does not ever run through my head, but it is useful for deriving other stuff. Okay, so what do I want to do? Okay, but now let me remind you, in the canonical, we have a bunch of relationships that are derivable, and in the grand canonical, we have similar ones. Okay, now this is a little funky, by the way. Here, I'm going to need to remind you that the partition function is the sum of states. E the minus beta u d plus beta. Okay, so, this is a little funky. In the same way that I proved this, and that was like a month ago, if I do something similar here, if I take the derivative with respect to u, what I'm going to have is something along the lines of the sum of states, beta probability of the state. Okay. Now, because of that, and I hate to do this to you, people like to express it this way. They like to take the beta, derive it out, divide it out, and then say that the derivative of the grand canonical, no, I'm not missing the minus sign. The derivative of the grand canonical with respect to beta u is average population of the, magic box or whatever it is we're describing. Okay, that kind of drives me crazy because there's two betas in the expression. And so that's kind of maddening. But reality is we're in a constant temperature. As in the canonical, the grand canonical is a constant temperature thing, and that means beta can be a constant. So it really should be outside of the partial, but people universally put it inside. That's fine. It's just that when I'm trying to take the derivative of this with respect to beta chemical potential, I'm flummoxed because there's a beta there too. And that really confuses the heck out of me. What's the derivative of a function with respect to xy when the function is e to the x, e to the y? What? Now, I don't know. That's very confusing. It's actually not confusing if y is constant. Then it's actually totally fine. But anyway, I just wanted to point that out because this is something that always confuses the heck out of me. So that's what's going on. Okay, now we also had, damn it. I need to actually put this, sorry. Now, we also had double derivative of natural log of q. And and that ended up being the fluctuation in the internal energy squared. Okay, likewise, if I do the double derivative of the natural log of the grand canonical, sorry, there, okay, again, noticing that the beta chemical potential deal is a little odd. I don't think I've already gotten some of the states the same way every time. I end up with a very similar expression. Now again, when that one day that I did this derivation on the double derivative of the canonical partition function being related to the fluctuation in internal energy, it's about a 20-minute step derivation. It's not terribly difficult, but we ended up with an expression that looked just like this. It's so similar that I don't want to redo it. Let me make sure I'm sorry, I can't do better than that. And this ends up being average of the square minus the average squared, which is of course the variance. The average of the variance. Okay, so what? Okay, so what is, I'm now actually able to prove PV equals nRT. With this information, I can prove PV equals nRT. So let me show you how I'm going to do that. And this is kind of neat because it's like a bunch of math tricks, but it's also completely accurate. It's stunningly accurate to do this. And what I'm going to do is I'm going to have a gas, and I'm going to put the gas in a box. And in my mind, or mathematically, or for real, for that matter, I'm going to partition the box into a whole bunch of sub-boxes, like 10 to the 24 sub-boxes. And I'll call that M. M is the number of little boxes. Okay. And I can't obviously draw enough of these. And I'm kind of going nutso with this because I'm trying to exaggeratively point out that I am discretizing space into a very, very, very small subset of little boxes. There we go. So I've got a volume in M boxes, where the boxes are about the size of a molecule, so you can't really fit more than one. And it's a gas, right? So there's not that many molecules to begin with. So it's like this. Now, the gases don't interact. That's terribly important. They don't interact. If it wasn't for that, I couldn't prove PV equals nRT. And let me show you what I mean. Okay. N sub I is the number of molecules in a box, in one of the M boxes. Obviously, it's going to be 0 or 1. The boxes are so small that they really don't have an option. You couldn't put 2 in there to begin with. The fact that it's dilute is kind of assures that. Number in cell I, number of molecules in cell I. It's either going to be 0 or 1. Okay, now what I want to do is to know the variance. Now again, I'm going to do this derivation because it's going to lead to PV equals nRT. Because I am looking at a variation in number, I have to do this in the grand canonical. Because in the canonical or microcanonical, n is fixed. So you must do this in the grand canonical. Okay, so what? Okay, so this ends up being, don't forget, n squared minus n squared. The average of the square minus the squared average, anyway. Okay, now that I've got this funny definition of a box, you've got to remember that n, here, let me do an aside here. All you have to do to get n is to sum m boxes and count the number of molecules in all the boxes, right? So brainless, it's brainless. Right, so that's easy. most of them are 0, but occasionally you'll find one, and you eventually find all n of them. Okay, now this guy ends up being a double sum. I'm sorry, we're adding up n boxes. That you can't use the same index. That's mathematically not allowed. You can't have both sums being I, because then that would be the same as this. Tell you what, let me, sorry about that, I tell you I'm never gonna do that, but I do it all the time, because I end up running my mouth. Let me express this as a double sum, and anyway, the average of the square minus the average squared ends up being this. I wanted to spend a bit more time explaining that, but it's hopefully kind of obvious, right? I'm hoping, because again, I talked too long, if this is obvious, and I hope it is, that this is n squared and that this is the average squared. I hope that's kind of obvious, again, because anyway. All right, now this is kind of cool. Number one, the average of any, when you look at the average of all of these boxes, for the most part, it's very small, right? Again, gases are very dilute, and for the most part, these boxes are empty. That means that on average, there's nothing there. Number two, now, this has to do with, remember, molecules, perfect gases do not interact, and they don't even collide because they don't interact. And in this model, what that would mean is that technically this is a joint probability. It means that these are equal. Now, I wish I had a little bit more time to go into this, but if you have a perfect gas that don't interact, where any I or J molecule is, that has nothing to do, where one molecule is has nothing to do with where that other molecule is. And that means that that these are the same. And I get a little flummoxed on that, but anyway, that is what that means. So this is a statement that I have a perfect gas. They don't interact. Okay, then what? Now this is kind of neat how this goes. I'm going to need the whole board. Okay, I need the whole board for this next part, so let me do that. And you're going to like this. This is kind of neat how this goes. And then I'll end with P equals nRT, which is just, again, a fluctuation of the density of a perfect gas. Now that I'm allowing density to fluctuate because I'm allowing the number of gas molecules to fluctuate, which is because I'm in the grand canonical. Okay, so I'm solving for, and what this ends up being is, see, the thing is that right here, you're going to have two different types of terms. Sometimes, think about A plus B plus C times A prime plus B prime plus C prime. There are n terms where, m terms, where I've got A times A prime, B plus B prime plus C times C prime. And so that is, doesn't matter what label I use. And then there's leftover terms, which is m squared minus m, ij. Right, I can do this. And I and j. And then I can subtract out the same. Okay, so this is this part right here. Again, this one has like A plus B plus C times A prime plus B prime plus C prime. This is the A times A prime plus B prime plus C plus 3 C prime. This is A times B prime plus A times C prime plus B times A prime plus B times C prime. Anyway, blah, blah, blah. Okay, so that's this, and this part ends up being the same. I've got a part where I'm basically summing across the same box. That's mathematically what's happening. And then I've got the leftover terms. Okay, so, all right. Again, just this thing, but I'm able to discretize it into two different things. A prime, blah, blah, blah. I'm kind of writing my mouth now. All right, so let's see here. So it turns out that these terms cancel each other. Okay. Now, again, remember, the reason I was able to write this is because of this right here. That's where that came from. And that's a statement of things being a perfect gas. Okay, now what have I got? I've now got something I equals M. Okay, minus just to remind you what we're doing. Okay. Now, this is actually, since there's a single sum, it ends up being quite easy. This ends up being M, average number in a box, 1 minus. Okay. So what I've done is, if I have simply M of these, then there you go, and then I just factored this. So that I have n to bi minus n to bi squared. That's what I've done. The sum is just gone and replaced with this m number of boxes. Ends up being quite trivial. Okay, now recall that I've used this once. What happened to this? Well, I can use it right here. Okay, so what that says is the number of the variance in the population of my box that is at constant chemical potential, and I do that by allowing molecules to come into and out of the box. The fluctuation of that is actually equal to the population of the box initially, which is kind of a funky thing. Now, let me show you, now this I think is actually really quite hard to digest. I'm actually not going to get to PV equals NRT. Let me show you what this does mean in terms of chemical potential, and then I'm actually pretty close to PV equals NRT. That actually only takes a minute, but I'm just going to end there. Let me just show you what do I do with this. What do I do with this is, recall that I started out with the derivative of the grand canonical partition function being very similar to the canonical partition function, except that instead of internal energy, I end up with n population. And this itself was equal to the fluctuation, which we now know is actually equal to m. Okay, therefore, I'm going to flip this expression here. And then multiply everything by v. Is that what I'm doing? Multiply everything by v. And what I end up with is the change in chemical potential with respect to density ends up being 1 over density. Where density is force N over D. Okay, now I'm going to stop here, but let me just show you what this means. Because this may all seem like just a bunch of, okay, I'm doing a bunch of derivations, but so what? We can play mathematical games with letters all day long. If we follow calculus rules, sure, we've done it right. This is horribly important. This is terribly, terribly, terribly important. And the reason is it tells me about chemical potential. It'll help if I wrote it the right way. How chemical potential changes. Now remember I was saying that chemical potential ends up being the thing in charge of chemical reactions. A simple chemical reaction is ice melting. Why does ice melt? It has to do with chemical potential. What's the chemical potential of the ice relative to water if ice is melting? Which has higher chemical potential? The solid, ice. Things that have higher chemical potential, if they can turn into things of lower chemical potential, they'll do so. So I've got a block of ice, and it's now 1 degree, it's melting. It's melting because water has a lower chemical potential than the ice. Chemical potential is the energy per mole, so that's why that'll keep on happening. Now, at 1 degree, all the ice will melt. Okay, fine. That's great. And the reaction of A and B goes to C. It happens because A and B have greater chemical potential than C. Now, if A and B completely react to C, that's because their chemical potentials were always out of balance. A and B always had higher chemical potential than C. Even as they transformed to C, that was still the case until all of A and B are gone and the reaction goes to completion. How many reactions go to completion? Not that many. Why not? Why are things imperfect? Because A and B, as they chemically react, their potential drops. C, the product, rises. That tends to be the case. Now, as the chemical potential of C rises and A and B drops, if they never equate before A and B are gone, the reaction goes to completion. If they do, it stops. So if A and B chemical potential drops as it reacts to C, and they hit an equivalence, the reaction stops. So maybe that yield is 50%. Now again, if they never equal chemical potential, A and B is dropping, but C is rising, but they never reach, then A and B will completely react. If halfway A and B's chemical potential equals to C, and we're at the halfway point, the reaction stops, the reaction has a 50% yield. That is where the finite yields come from. There you go. This is actually telling you that. I know it's a little hard to see. So again, reactions having finite yield is one of the most important things that physical chemists can know. It comes from chemical potential, all the things I just said. This is actually telling you that. It's hard to see, but it tells you that. So now look at this. Chemical potential changes with density. Does it go up with density or down? Think about it. Does it go up or down? If density rises, does chemical potential rise? You should be able to tell me from what I've shown you. Does it go up or down? So, density is rising. Does chemical potential rise or fall? Okay, that would have a negative derivative, right? You said it falls.
So is this where the math is?
This is middle school math. Chemical potential, density. You said if density rose, chemical potential falls. You just said that, right? That means that the line has a negative slope. This is the slope. It's 1 over the density. Is density negative? 1 over density negative? So did you get it right or wrong? Wrong. You got it wrong. Chemical potential always rises with density. This is, again, I told you, this is more important than it seems. Chemical potential only can go up with density. It is inherently positive, it cannot be negative. Now tell me this. How do I increase density? Now, increasing density increases chemical potential. How do I increase density? Now remember, the volume is constant in the grand canonical.
Increase the mass.
Increase the what? Mass? And how do I do that in this world? Increase
the number of particles.
Increase N.
N.
Okay. Now tell me, big picture, how does chemical potential change if I add more stuff to it?
Chemical potential is
Increase.
Increase.
Yeah.
Yes, chemical potential, if I have a box with N in it and I add more, the chemical potential goes up. If I take it away, chemical potential goes down. Now, I just said A and B are reacting and they go away. Does their chemical potential rise or fall? Falls, because they're leaving. It's as though I'm taking them out of the box. C is rising. Why?
Amount is increasing.
Because the number of moles is increasing. Its chemical potential rises. And if they equal, the reaction stops. That's why reaction yields are finite. The most important thing a chemist could know. Why don't reactions go, why do they go? And if they go, why don't they go all the way? It's right here. You just learned why. Anyway, okay, next time what I'm going to show you is that this can be manipulated, literally, sorry, I went way over. This can be manipulated in just 2 steps to show P equals nRT. But I've gone over cell stuff. Yeah.